Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 27, 2026, about 4 days ago. It proposes a new set of loss functions called LK losses that replace standard objectives in speculative decoding, improving average acceptance length by up to 10% on coding and math tasks. The paper is titled, LK Losses, Direct Acceptance Rate Optimization for Speculative Decoding. And as we'll see later, these results hold true across a wide range of model sizes, from 8 billion all the way up to 685 billion parameters. On Hugging Face, the 13 billion and 3 billion parameter models are ready for download, including VLLM usage examples to help you optimize speculative decoding performance today. To see these gains in action, Figure 1 plots the average acceptance length against the maximum draft length for the Eagle 3 architecture. The green line represents the standard KL divergence baseline used by most current systems. Above it, the blue and orange lines track the new LK loss variants. These proposed methods consistently achieve higher acceptance lengths. And interestingly, the performance gap widens significantly as the draft length increases beyond 4 tokens. Well, Figure 2 illustrates why standard objectives fail for small models. It compares how different loss functions fit a simple orange draft curve to a complex target distribution. On the left, minimizing KL divergence forces the model to spread out thinly, resulting in poor overlap and only 50% acceptance. In contrast, the rightmost column shows the total variation objective. This approach prioritizes the actual green overlap area, finding a solution that maximizes acceptance to over 60%. Moving from theory to results, Table 1 validates this intuition using the Llama 3.18b model. It reports average acceptance lengths for Eagle 3, Medusa, and MLP architectures. Focusing on the Eagle 3 section at temperature 0, standard KL training achieves a score of 3.75 on Mount Bench. In contrast, the pure total variation loss fails to converge well, dropping performance to 2.81. The hybrid LK loss solves this, delivering the best results across all tasks, which confirms that balancing the objective is key. Expanding on those initial findings, Table 2 demonstrates that these gains hold up across a much wider range of target models. The list includes architectures scaling from Llama 70B all the way up to the massive DeepSeek V3. Notice the distinct performance shift between the temperature settings. The relative improvements, shown in parentheses on the right, are consistently higher at temperature 1. For example, looking at the QN3 model, the LK loss boosts mean acceptance length by over 8%. Similarly, the DeepSeek V3 results at the bottom show a steady 5.6% gain, confirming the method scales effectively. So Table 3 explains the mathematical reason why the pure total variation loss failed to converge in the experiments we just discussed. It breaks down the gradient strength when the draft model is still uncertain. Look at the middle row for T versus loss. The gradient on the target set S scales with 1 over versus. Since the vocabulary V is massive, this value is tiny, causing the gradients to vanish. However, the LK loss in the bottom row fixes this by scaling with 1 over K, matching the strong learning signal of the standard KL divergence. Following the gradient analysis, this detailed table compares the new approach against established community checkpoints, labeled here as HF. In the top section for Llama 3.18b, the LK-trained models consistently outperform the external baselines, scoring 4.89 on human eval compared to 4.49. Skipping to DeepSeek V3 at the bottom, the gap widens further. The proposed method reaches a 4.0 acceptance score on MT Bench, significantly surpassing the community alternative at 2.9. Alright, to conclude, the big takeaway is that standard training objectives often mislead small draft models, while directly optimizing the acceptance rate yields significant speedups without added cost. This shift could fundamentally improve how we deploy large language models, making inference faster and more efficient. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.